Hello, this is Michał Wójcik here, and I welcome you to my series of lecture Physics for Amateurs. And today we will start doing some physics. We will consider a set of n particles. Each of the particles, each of the particle will be denoted as vector qi, let's say. There will be n of particles, so this is a very generic case. Obviously, our vectors are three-dimensionals, and we will consider trajectories. So this qi here will depend on time. Let's imagine they all depend on time t. I will note it here, depend on t. Right. For convenience, we will put all of them in one, let's picture it as one big column vector. So let's say that will be one big column vector of column vectors, which simply means we will have for three coordinates each particle will occupy three coordinates. And so on till the last one, till the nth one. We are not losing any information by putting them all in one big column vector, because you can always say, you can always tell to which particle given coordinate belongs. So the fourth coordinate of this big column vector will be first coordinate of the second particle. The third will be third coordinate of the first particle. So we are not losing any information by putting all coordinates of all particles in one big vector, but that will give us just one symbol to operate with, which will be pretty useful. Now let's consider forces that will act on our particles. So let's just call these forces conventionally as F, and force acting on each particle will have the same index, and obviously if we consider them as trajectories, the force acting on a particle will depend on time, because we may ask, what is a force which acts on a given particle in a chosen point of time? But we might require that the force will depend on position, but not necessarily on the position of particular particles. The force might depend on the whole configuration. So the force might depend on position of all particles in this setup. So if we will build another big column vector by analogy to this one, which will consist of all column vectors of force, we might say that this will be a very generic case of force field, when force, understood as this big column vector of forces, will depend on a position in this 3n dimensional space, because the position, this big column vector will have dimensions 3n, and force will depend on a position in this big space. So for each, by this description, whenever our particles will occupy the same positions in the space, but I mean all of them the same positions, we will know the forces which act on them. If one of them will change position, there may be change for all forces, because all force vectors will depend on a position of all particles, and we might think here as that all particles, with each is described by 3 dimensions, we might consider them conceptually as a one particle in 3n dimensional space. So now, how force will depend on position? Today, in our example, it will depend on a very specific way, but the way which will turn out to be a very generic way. So let's imagine we have V, which maps our 3n, so our 3n dimensional Euclidean space, into R. It doesn't need to map the whole space, it might map only some region of this space that we need, but nevertheless, V is mapping positions of all our particles in a one real number. So obviously, if we would like to denote V, might be considered as a function of all positions, we might use another letter here, because if we consider Q as our trajectories, we might use a letter X just for position, but usually we don't do that distinction. Obviously, it is a matter of convention. We might write V as a function of multidimensional real vectors, and so on. So this is a function which has 3n arguments. And now, what we will require of f? Simply that f is equal to let's use x here as to denote a point in our 3n dimensional space. This is our assumption. There is some function v which maps positions into some real number, and we want our force to be equal minus of derivative of f with respect to x, which obviously is a very long column vector, which means that this derivative will be, in fact, in our previous convention, that will be now row vector, but we will not stick to that because it will be mixed anyway when we will start to multiply, take a derivative of q and multiply it by m, then we need to anyway see this as sometimes as column, sometimes as row, so we will not be too attached to what orientation of column it is, or what orientation of vector it is. The most important thing is, by our definition of derivative, this is a 3n dimensional function. If we still denote it now in a column convention, that will be x1 1, x1 2. These are just partial derivative with respect to subsequent arguments. And so on for all coordinates. And this is our assumption. By that, because v depends on position in this 3n dimensional space, f will also depend on position in this 3n dimensional space, which means for a given configuration of our particles, we will always know what are the forces which acts on a particular particle. And we call V potential energy. And why is that? We will go to that. Why is that? Because there is a very important reason. Why is that? Let's calculate the work which will be done by forces of this force field when we will move all particles from one chosen positions to the others. So let's assume that at time t0 all of our n particles will be in position q0. The q0, remember, is this large vector of 3n dimensions. And then at time t1, all particles will be in a position q1, another big vector of 3n dimensions. So from time t0 to t1, we will somehow move all particles from q0 to q1. And q, depending on t, will simply denote the trajectory of all particles. We might write it here as a two-dimensional picture, but what we really mean is that this line represents the movement of all n particles. So we might think about this as a line in space of 3n dimensions. Now, what is the work? How we measure work done? It's force times space shift. So if we move an object, we multiply force which acts on that object by space displacement, and this gives us the energy, or the work measured in energy, that was done for this object. So if we write an integral where f is our force, a 3n dimensional vector of force, and that will be our vector of all infinitesimal displacements, and the multiplication here is a scalar multiplication. So at each point we multiply displacement by force, and we have infinitesimal parts of energy. Now, if you want to think about it as an approximate summation, it will be our force at some point qi. Let's put I in upper index because we use already lower index. That's just some point on trajectory times f is a vector times very small displacement, which we will make when we move our particles a bit. And obviously, if our displacement will converge to 0, that will convergence to our integral. So that's the understanding of this integral. Now, obviously, this integral, it's a bit hidden here, this t dependence, but we integrate along our trajectory. We integrate along trajectory, even if t is not written here. Now, what we know about f? We know that f is given by some function v as a derivative over argument which is 3n dimensional. So we can write this is scalar multiplication. And now, by using chain rule, we're simply getting that this is integral from q0 to q1 over the trajectory df, and that obviously is v q0 minus v q1. Now, if you have problem with accepting that, let's continue on our summation. So we wrote the force as our derivative with respect to q at point q1, qi, but this is not very important here, times a scalar product of a small shift of q. But what is this? If we remember what is derivative, we have just it's v qi plus delta qi minus v qi. This is obviously approximation, but the relevant theorems are obviously proved in mathematics. But this is qi plus 1. So if we add all of them together, this qi will be cancelled with the previous summoned from this sigma. So we will be left only with first and last term. There's minus sign here, so we need to invert them, and that will be q0 minus v q1. And this is exactly what happened here, because we know that by chain rule, if we operate on derivatives, that will give us just dv. So it turned out that the work done doesn't depend on the trajectory. So the trajectory could be like that, the trajectory could be like that, it doesn't matter because this integral depends only on the first and last value of f, of v, at point q0 and q1, which are just start and end point of the trajectory. So if the force is given by the derivative of some function v, the work done by the forces on the system of particles depends only on the difference between v of the starting point of the trajectory and ending point of the trajectory. And this is why v is called a potential or potential energy in that context. Let's show this on a very important example. So we will consider again n particles, and that will be in fact planets, because we will be talking now about gravitational potential, and we will show how to calculate Newton force, for a force from a Newton law of gravitation from this potential. So let's think about planets in solar system or in any other constellation of bodies in the universe. So yeah, let's Q1 to Qn will denote our planets, our bodies. And now they will denote the positions. So each of them is a three-dimensional vector. Now, to write a potential, first introduce a very useful value, which will be simply a distance between body I and body J. And now we will write a potential function G, which is gravitational constant, Mi, Mj, which are masses of corresponding particles, time R divided by Rij. Let's pause on that for a second. V is indeed dependent on positions of our particles. So V is a function which maps Euclidean space of dimension 3n into real numbers. It takes each combination of our particles, takes its masses, multiply, and divide by the distance. And we take 1/2 here, because in this summation we took each pair twice. So this is our potential. It doesn't really map the whole space into real values, because some parts are forbidden, because when Qi will be equal to Qj, obviously R will be 0, so we can't divide by 0. So some parts of the space will be forbidden, but from the physics perspective, they are not so important. Mathematically, they will be very important, and we will go to that at some point. But for now, we are simply assuming that our bodies can't occupy the same place in the space, so we will not have a problem of r equal to 0. So our v, as we established, depends purely on positions of our bodies. Now, let's calculate force which acts on body I according to the rule that we know that F is equal to minus derivative of F with respect to Q, which is a very long vector of all coordinates of all particles taken together. To calculate it, we need to be a bit more detailed, so we will calculate kth component of the force acting on ith particle, which is obviously a minus derivative of f with respect to q I k, which again represents the kth component of the vector which describes position of the ith particle. Now we will need to replace I here because we used it already here, so we will replace it by L, let's say, and we will leave minus here, and we will use it at the very end, as I think. Let's leave 1, 2, and G before summation. Let's write derivative now, and let's write summation using L, J. So L is different than J, and we will consider all ML, MJ divided by RL, J. Now, let's think about it for a while. Only these parts of this summation, which depends on QIK, will contribute to the derivative. Those which are not dependent will simply vanish. So we might replace this sum by different sum, IK, which will iterate J from 1 to N, but obviously without I, MI times MJ divided by RIJ. And why is that? Because all others will vanish under our derivative. So we care only about those terms here where R depends on I. So let's go with derivative under the summation, but before we do this, let's here write Rij in a bit more explicit form, which will be the summation of squares Jm, summation of squares, and obviously we've taken a square root of the summation of squares, which is simply a distance between two points, which are described by 3 coordinates. So now we will put this here. R is in the denominator, so there will be minus 1/2. Let's start with here minus 1/2 g. We will write our summation symbol. J can't be equal to I. We can put mi, mj before, as they are constant, before derivative. Let's write our derivative. And here we will have simply this expression, qi m minus qj m squared to minus 1/2, because r is in denominator. So now we need to think what is the derivative of this expression with respect to qik. We will use a rule of calculating derivative of the composition of functions. So we need to take a derivative of outer function times derivative of inner function. So what will be derivative of outer function? That will be this, 2 minus 3/2. So let's rewrite mi, mj. Now just rewriting outer function, and now to minus 3/2, because that's the derivative of the outer function. And we will write here derivative of inner function. Just a sum of squared. Now, if we think about this, only for m equals to k, derivative of this expression will be not 0, so we need to take care only about this. And here again we use the rule derivative of outer function times derivative of inner function, but derivative of inner function here will be simply 1, So that will be just derivative of outer function, and then we have expression we'll leave mi mj. That we will write going back to r, so we can put it again in the denominator. Mi mj divided by r ij to third to power 3, just because here we have minus 3 over 2, and that is simply derivative of outer function, but only with k, because all other parts vanishes. To cancel out. Now remember about this minus, we will use it to swap qi with qj, so there will be no longer minus here, but those will be swapped, and we will go back with j under the summation. Now qj k minus qi k, which is a difference of kth components of the vectors of the particle j and particle I. So if we want to write an equation of force ith, which means the force which acts on the ith particle, we need to put together all components of the vector, and our equation will look like this. Qj minus Qi. And this is summation over all particles which are different than particle I. This obviously, if we look at one component of this, of one summand of this summation, so then if we write auxiliary force Ji or Ij, I prefer Ij, it doesn't really matter, but we will have reverse order here. Ij, if we introduce auxiliary force J and Mj, the third Qj minus Qi. What we can say about this force Ij, and obviously the force acting on particle I is a sum of all forces Fij. So what is the force Fij? First of all, if we picture here a particle Qi and particle Qj, I forgot they were planets or bodies, but I still call them particle. But you know, in a cosmic scale, planets are like particles, so it's really the same. So first of all, this force acts in the same direction, or more precisely, the arrow of this force is the same as arrow of this vector, which is towards particle Qj. And the magnitude of this force is obviously G times mi mj divided by rij squared, because the magnitude of this is simply a distance between particle j and particle I, and here in the denominator we have r to the power of 3. So this cancels with 3 and leaves us 2. And this is a Newton's law of gravitation. The force with which object J acts on object I is equal to gravitational constant times multiplication of masses divided by the square of the distance. And in here we just have a information what is the arrow of the force. So this is simply a law of gravitational attraction. And to calculate the total force which acts on particle I, we need to add up all forces which acting on I from all bodies in our system, obviously except of I, because I doesn't act on I with the gravitational force. So let's go back. We took potential, which is just a function of positions. It depends on positions. We took potential according to this expression, and we calculated that the force, which is a derivative of this potential with respect to position, is exactly the gravitational force. It's a force according to the law of gravitation. So now if we remind our previous reasoning, which tells that if we move our particles from one configuration to the other, the work that the forces do are equal only to the difference between potential at the start point and the end point. So we showed here that gravitational forces between n bodies have potential function. That means this law applies to gravitational forces, which means that it doesn't matter what are really trajectories of the particles. If the system is moved from one configuration to the other, the amount of energy that was used as work by gravitational forces can be calculated just by taking a difference between potential at a start configuration and at end configuration. And this is kind of amazing result that gravitational force has this property. Later, when we will talk about Lagrangian picture of classical mechanics, we will show that the trajectories in the system of particles are the trajectories of least action. And the action will be defined as kinetic energy of all particles minus potential. But we will go to that in the next lecture. That's all for today. Thank you very much for watching this. I hope you enjoyed.